Okay, let's dive into this. In nature, some designs, they're just so good, so fundamental that evolution can't seem to let them go.
Right.
It keeps coming back to the same idea.
Mm.
And today we're talking about maybe the ultimate example of that, a real evolutionary superstar, the crab.
It really is. I mean,
Mhm.
that classic crab shape, squat, armored, wide. It's one of the biggest success stories ever. We're talking hundreds of millions of years. This design has been, well, in fashion.
Right. And it's so effective that it's evolved over and over again. Someone even called it evolution on steroids, which kind of captures it, doesn't it?
It does. It's this tendency for creatures to become crab-like.
And that's our mission for this deep dive, right?
Right.
To figure out why. Why this specific body plan, this crustacean tank design, how did it evolve independently so many times, even in species that aren't really close relatives?
Exactly. And there's actually a term for that. The general phenomenon is called carcinization, just
Yeah.
things evolving to look like crabs.
Carcinization?
But if we're talking specifically about the evolutionary path within the decapod group, shrimps, lobsters, and true crabs, then the term is brachyurization.
Brachyurization. Got it. So specific to that family line, and the sheer scale of this is just huge. This isn't some minor adaptation we're looking at.
Oh, absolutely not. It's a global strategy that's been working for, well, over 260 million years. Think about it. Today, there are something like 9,500 living species that fit this mold.
Wow. 9,500.
And the fossils. We know of at least 3,300 extinct ones. It's a biological dynasty, really.
It truly is. So, okay, to understand why it's so successful, we need to break down the design itself. What actually makes a body plan crabby?
Yeah. What are the core features? What defines that crab look? If you were an engineer looking at how you get from something maybe more like a lobster to this compact form.
Right, like what are the trade-offs? What do they gain? What do they lose?
Well, they definitely prioritize defense and stability on the ground over, say, fast swimming in open water. It really boils down to three key characteristics.
So what's the first?
First, that hard upper shell, the carapace, gets flattened and, importantly, much wider, creates that iconic shield shape.
Maximum protection covers everything. Makes sense.
Second, underneath, they developed a really broad, strong sternum. Think of it as like a wide chassis or stabilization plate on the underside.
Okay, so a solid base.
And the third one, this is probably the most critical change. The tail. Or, well, the pleon, technically.
Oh, yes, the tail bit.
In a crab, that long, often vulnerable segment is folded right up underneath the body. And crucially, most of the muscle, the powerful swimming muscle you'd find in a lobster tail, it's gone.
Right. If you think about eating lobster or shrimp, that big tail muscle is the main event, right? That's the valuable part.
Exactly. That's the engine for that rapid backward flick they do to escape.
So crabs basically gave up their escape rocket.
Pretty much. They traded that powerful propulsion for, well, a structural component that tucks everything away neatly and keeps a low profile, heavy armor, better ground maneuverability.
A walking fortress instead of a swimmer.
Yeah.
When did this start showing up?
We see the beginnings of this shape in the fossil record back in the Jurassic period. But the real explosion, when crab diversity just took off and they became, a dominant force, that was during the Cretaceous period. Started about 145 million years ago.
Okay, let's trace that family tree a bit because crabs didn't start out looking like this. They belong to the order Decapoda, right? The 10-footed animals.
That's right, Decapoda. It's a huge group, includes shrimp, lobsters, crayfish, and all the crabs.
And the 10 feet. That's not literally 10 feet like we think of them.
No, it refers to 5 pairs of appendages used for walking or manipulation. So usually 4 pairs of walking legs, plus that front pair that's often modified into claws, the chelae. Pincers.
Gotcha. Claws count as feet in this context. So the ancestor of all these decapods way back when must have looked quite different.
More.
Elongated.
Oh, definitely. Ancient decapods had long bodies, prominent tails, very exposed. We have fossils like Paleopelemon.
Paleopelemon.
Yeah, lived around 365 million years ago, late Devonian period. It looked much more like a modern lobster than a crab. Long body, long tail.
So if they started out like that, like little underwater stretched out things, when did things split? When did evolution start seriously pushing towards the crab shape?
That big divergence seems to have happened around 260 million years ago. Decapods sort of split into 2 main branches, both heading towards crabbiness, but in slightly different ways.
Okay, 2 paths to the same destination.
Exactly. The first group are the Brachyurans. These are the ones we call the true crabs.
Ah, the Brachyurans. True crabs.
They are by far the most successful decapod group today. They've conquered pretty much every environment, deep sea, coral reefs, freshwater rivers, even onto land.
So when we talked about brachyurization earlier, that's the evolutionary path
Right.
specific to these guys. The fiddler crabs, spider crabs, mud crabs, all those.
Precisely. They followed that direct evolutionary line to the classic crab form. And the earliest true crab fossil we found so far is a little guy called Oprosopon klugi.
Eoprospon.
Yeah, it dates back to the lower Jurassic, about 185 million years ago. Clearly on that true crab path.
Okay, so that's path number one. The Brachyurans, the true crabs. What's the other path?
The other major group are the Anomurans. You can think of them as the false crabs.
False crabs.
Okay.
So they look like crabs but aren't true crabs.
Exactly. They arrived at a very similar body plan through convergent evolution, a parallel path. This group includes some really well-known creatures, porcelain crabs, hermit crabs, squat lobsters, and the giant king crabs.
King crabs are false crabs. Interesting.
Yep. Anomurans. They achieved that crab-like form independently, and their lineage might actually be even older in terms of starting down this road. The earliest known ancestor is Platycota akakina.
Platycota.
Dates back to the late Triassic, maybe 250 to 200 million years ago. And interestingly, it looked more like a lobster initially, so it shows that transition happening in their line too.
Wow. Okay, so this is key for anyone listening who might be, rock pooling or at an aquarium. You see something that looks like a crab.
Yeah.
How do you tell if it's a true brachyuran crab or one of these false Anomuran crabs? They look so similar.
There's actually a pretty easy way to spot the difference. Usually it comes down to the legs.
The legs. Oh,
Count the pairs of walking legs you can clearly see behind the big front claws.
all right. What am I looking for?
True crabs, the Brachyurans, they have 4 pairs of visible walking legs, 8 legs total plus the claws.
4 pairs.
False crabs, the Anomurans, they look like they only have 3 pairs of walking legs, 6 legs plus the claws.
Only 3. Where did the other pair go?
They still have them, but that 4th pair, the last pair, is usually much smaller, shrunken down, and it's often tucked away, sometimes hidden up inside their gill chambers. It's not used for walking.
Huh. So it's like a little hidden leg pair tucked away. That's a great field mark.
Hmm.
Count the walking legs. 4 pairs visible means true crab. 3 pairs visible likely means false crab.
It's the most reliable visual cue. Another little clue, though maybe less consistent, is the antenna.
Oh, yeah.
Anomurans, like hermit crabs or king crabs, often have longer antennae, and they tend to be positioned more off to the side of the eyes. True crabs often have shorter antennae, maybe more between the eyes, but the leg count is the main thing.
That makes sense.
Mm-hmm.
And you mentioned king crabs or anomurans. Do we see fossils showing their line becoming more crab-like over time?
Oh, yes. A good example is an extinct one called Paralomus debodiorum.
Paralomus.
Yeah, it's an ancient member of the king crab family, the Lithodidae, lived around the Miocene epoch, say 16 to 5 million years ago, and it definitely has that characteristic nubbly armored carapace, showing that continued push toward the compact defensive shape within the Anomuran line.
It's just incredible how evolution keeps landing on this same solution. Which brings us to maybe the most mind-bending part.
Mm-hmm.
This crab shape is so good, it's not just decapods doing it. Other creatures, completely unrelated, have adopted it too.
Right. This is carcinization happening even outside the whole shrimp and lobster family tree.
And the most famous example has crab right in its name, but it's totally misleading.
You're talking about the horseshoe crab.
Exactly. The name is basically a lie, isn't it?
It's a total misnomer. Horseshoe crabs are not crustaceans at all. They're not decapods. They belong to a completely different group called chelicerates.
Chelicerates. So what are they related to then?
Spiders and scorpions, believe it or not. They're much closer relatives to spiders than they are to any true crab.
Wow. Spiders. That's wild. But they definitely have that wide, armored, dome-like shape. How long have they been around?
They are incredibly ancient. Their fossils go back something like 445 million years, Paleozoic era.
445 million years. That's way before, well, before most complex life on land.
Absolutely. They were rocking that armored tank design long before the dinosaurs, long before trees really took over. And that basic shape has clearly served them well. They've survived multiple mass extinctions and are still with us today.
Okay, so we've established it. Nature loves this shape. True crabs, false crabs, even spider relatives end up looking like this. But let's nail down the why. What's the core advantage? Why is this better than being long and potentially faster like a lobster?
I think the main driver is probably superior stability and localized mobility, especially on complex surfaces.
Stability and local movement. How does the shape help with that?
Well, that squat, wide form gives you a really low center of gravity and distributes weight evenly. Think about trying to walk over uneven rocks or through shifting sand or mud. A long body might tip or get snagged. The wide, flat crab shape is just much more stable.
Right, like a little all-terrain vehicle.
Yeah.
Harder to knock over, better grip.
Exactly. And by tucking that tail away, they eliminate a potential vulnerability and create that solid, protected base. They might sacrifice that explosive backward swimming speed.
The escaped rocket.
Yeah, they trade that for being really good at maneuvering in tight spaces, feeding effectively, and hiding quickly on the seafloor, which is where most of the action and danger happens for them. Plus, they're carrying that wide shield of armor everywhere.
It really is the ultimate defensive posture for life. On the ground, underwater. It's like the optimal design for, I don't know, benthic warfare.
That's a good way to put it. Oceanic ground warfare. That's the crab blueprint.
But evolution's path isn't always one way, right? It can backtrack. If the crab shape is so good, has anything ever, bucked the trend, evolved to become less crab-like? Is there such a thing as decarcinization?
Yes, absolutely. It's much rarer, as you'd expect, if the crab form is so advantageous, but it has happened. We know of at least 7 instances where crustaceans seem to have evolved away from a crab-like form.
7 times. So they achieved crabbiness and then gave it up. Why?
That's the puzzle. Maybe they moved into a niche where the crab shape wasn't optimal anymore, perhaps favoring swimming again? It's an evolutionary U-turn.
Is there a standout example of this decarcinization? A creature that really broke the mold?
There's a fantastic one that was discovered relatively recently, actually. An extinct species called Calicimera perplexa.
Calicimera perplexa. The name sounds intriguing.
It means perplexing, beautiful chimera. And it really was perplexing. Lived about 90 million years ago, Cretaceous period. It was tiny, only about the size of a quarter.
A quarter-sized.
Yeah.
Anti-crab. What did it look like?
It had features that just don't fit the crab mold. It had these large, almost paddle-like legs, suggesting it might have been a swimmer again. Its body was relatively long compared to its width, and most strikingly, its tail wasn't tucked under. It was exposed.
Wow. So it really did undo those key crab features. Paddle legs, longer body, exposed tail.
Yeah.
Like it was experimenting with a whole new design.
Exactly. It threw out the standard crab rulebook. A fascinating example of evolution trying something different, even if that something different was moving away from a previously successful design.
It's just amazing how flexible evolution can be. But what's also incredible is how relevant this ancient crab design still is. We humans often look to nature for engineering inspiration. And the crab, well, it hasn't gone unnoticed.
Not at all. That elegance and efficiency of the crab form, it's directly inspired modern technology, particularly in the field of micro-robotics. Tiny robots.
Tiny robots based on crabs. Tell me more.
Yeah, engineers, I believe, at Northwestern University specifically looked at crabs when designing these miniature machines. They didn't just pick any crab either. They focused on the peaky toe crab.
The peaky toe crab, why that specific one?
They analyzed its structure and movement, recognizing that its particular combination of a wide, stable body and the mechanics of how its legs bend and move offered peak efficiency for walking, turning, and navigating complex terrain at very small scales.
So they copied its biomechanics.
Pretty much. They created these remote-controlled robots that are only about 0.5 millimeter wide. Tiny. By mimicking the crab's design, its rigid shell segments connected by flexible joints, these little bots can do amazing things. They can bend, crawl, walk sideways like a crab, turn, and even jump.
Jump. Tiny crab bots that jump.
Yep. All inspired by the peaky toe crab's efficient mechanics.
That's incredible. So this design, honed over maybe 260 million years on the seafloor, is now the blueprint for robots smaller than a flea. It really speaks to how optimized that wide, armored, stable form is.
It really does. It's just a masterclass in natural engineering, proving itself effective enough to evolve independently multiple times and now inspire our own technology.
A true testament to finding a solution that just works, again and again.
And it leaves you with a fascinating thought, doesn't it? If this crab-style guide proved to be the ultimate answer for mobility and survival in the ocean across vast stretches of time, what other ancient body plans, maybe ones we think of as primitive or long gone, are just waiting for the right conditions to make a comeback? Could we see something like a sea scorpion design reappear, or a trilobite form, if the environmental pressures line up just right in the distant future?
Evolution's greatest hits on repeat. That's definitely something to ponder.